What's up, CS32 instructor? This is my final turn-in for Pset 5, and yeah, let's get into the code. Into our directory, our movie database, which is really just a dictionary. So what we did was we opened the movies file that we had in here, and we wanted to tell Python how to read the characters in the file. So we put this thing here, encoding equals UTF. /8. This just tells Python how to read the characters in the file. We created a reader that reads the file as a dictionary, and then we looped through each row in that file that we just opened using this for loop saying for row in reader, so looping through each row. And we wanted to, so we're going through each row in the file which we're reading as a dictionary. So here, we're creating the ID into an integer. So we're turning the ID of the movie into an integer. Then we're gonna store the movie details into the movies dictionary using that ID that we just converted as like the key. So what we did, we stored the movie title in row title, the year in year, and then we created a set to hold the stars IDs that were in that movie. And it just iterates through all those, uploads all our data into the movies, and we're good. Now, for step 6, we want to create a build functions function, or build names function, sorry. So what we did here, this is really pretty simple. Initially, we want to loop through each person in the people dictionary. So for person ID, that person in the people, the items in people. So we converted every name to lowercase just to make sure that we're not finding any errors. Like you can spell the person's name however you want. And if the name is not already in like a key in the dictionary, then it needs to create the name with the ID and just add it to the dictionary. So if the name's not already in there and doesn't already have an ID, we can add it. But if the name's already in there with a different ID, we just add that ID to the name. So it's one person with two different IDs, but it's still the same person. And yeah, that's our build names function. That's step 6. So now step 7, what do we want to do here in step 7? Okay. So for step 7, we created our find path definition. So for our find path, we wanted to create a function that had a start parameter, so a start person that we wanted to, a start actor that we want to start at, and a goal actor, and we wanted to find the list that pairs the start ID to the goal ID. And if the path is not found, then it returns none. So initially, this is just sanity check, make sure we're not putting into the same people. We'll talk about the frontiers later, either a deep search or a breadth first search. And yeah, I didn't need to. Okay, never mind. So initially, this is what we're gonna do. So we wanted to create the very first node because we have to start from somewhere. So we're creating first node with the start actor that we inputted at the start. It has no parent because it didn't come from any other ID. It just was the starting one, and it didn't have any action. So like nothing happened for it to come here. We're just creating it. Then we're adding the first node to the frontier, and then we're creating explored, which is a new set that needs to keep track of the explored IDs that we have, or the explored actors that we have explored. So while the frontier is not empty, so we just need to ensure that, we still have nodes to explore. If we still have nodes to explore, then we just need to remove the node that we're exploring at the moment, and then we're gonna explore that node, see what's happening, see if it has neighbors, see what's going on. So what we wanna do here, we said if the node state equals the goal, so if the node state is where we wanna be, then what we're gonna do is create the path, so just a set of the path at how we got there through the IDs. And then we're gonna say, while node parent is not none, so when that node came from another node, so when we still have gone through the list, it's not the end of the list, we're still in the middle of the path trying to find the end, we wanna attach the node into path, attaching the action that it took to get there and the state, so the current step, and the current state and the current action. So our next node equals the parent of that node. So we're really just moving on to the next node after we've added that node into path. And then it's going to keep doing this until it's found the whole entire path. And then it's going to reverse it so we can find start to finish, because this would really tell us that it's going from the back to the start, and we want the start to the back, or the start to the end. Here, I'm pretty good on time. Okay. And then, yeah. And now, once we do that, we return the path. If this is not true, then we just add the node to the explored. So we just add it to our set explored to say we have explored this node. There's no need to explore this node again, and it wasn't the goal. So now we're going to keep looking at this node, and we're going to look at the people who've starred with the current person. So we're trying to find the neighbors of this current person that we're exploring. And this is using this right here. So for movie in people, we're checking the state. And for person in movies, we're checking the stars that it went with. So we only want to add the neighbors that haven't already been explored and that aren't in the frontier. So if this person, so our node, if it's not explored and not in the frontier, then we want to make that node a child. So we want to create this new child node and then we're going to input its state, so the person, who it is, the parent node, where it came from, and the action. Now we want to check if the neighbor is the goal. So if this neighbor is the goal, then we want to do the same thing we did before. So path equals the empty set, and while there's no child parent, so like while the child didn't come from anybody anymore. So if we're still in the middle of the thing, if we're still in the middle of our list trying to find back towards the start, then we want to add it again to our set. This is exactly what I explained before. And then whatever added to our set, the new node or the new child is now the parent, and we want to reverse this path and return the path. And then if that does not get triggered, if the child state is not the goal, you just add it to the frontier, because we can explore that later, but it's not the goal. Okay. So now, 30 seconds, or minute 30. So now, we're going to run DFS on this. Okay. So make sure we're good here. We're going to go Demi Moore. And we're going to go Mandy Patinkin. And look there's running a DFS search. We found 3 degrees of separation. And yeah. Now, we are going to explain step 8. So in step 8, what we did was So practically what we did, we wanted to create not a DFS search, but something that would allow us to make a BFS search. So what we did was we created this new class that inherits all its info from the stack frontier that we used before, but it makes sure that we use first in, first out instead of last in, first out. So so let's explain the code. So we're just finding remove function. If the frontier is empty, we can't remove anything. So we're just saying exception, whatever. If it's not, then we get the first node in the list, and then we take the first node in the list, and then we're gonna remove the first node from the frontier by slicing it out of the list, and then it updates the frontier so it contains everything after that first node. And that's the node that we're exploring. It takes all the information, so it returns this node that was sliced so it can be processed. And now, so let's run it with BFS now. And again, running the BFS search, it still found that it's 3 degrees separation, but it found a quicker way. Well, not technically quicker because there's only 3, but it used different people. It used Gary Sinise instead of whoever used before. So that was step 8. And now, just want to show you that something is not connected here. So we're going to run Demi Moore, Emma Watson, and just showing you that here, these two people, Demi Moore and Emma Watson, are not connected at all. And so yeah, now I'm a little over time here, so I'm gonna try to keep this short, but in step 9, when I used the large data set, when we used the large data set, it found a path, but the DFS was very much more inefficient than the BFS. So my BFS, it found a path instantly. It was a one degree path that it found. But the DFS, it found like a path, but it was 650 degrees long, super inefficient, took super long. The reason why this happened, I think, because it initially just chose the wrong path. So when it chose this wrong path, it went all the way down to try to find the end. When it did eventually find the end, it found a path, but it was just way too inefficient. With BFS, it checks every single neighboring node to see if it's the right one, and it was the right one. So first degree separation, it just found it. So this is why it's super inefficient, and yeah, that's what I think. So thanks for listening. I hope this is about 10 minutes in length, and see you later.